Welcome. Today we're going to continue our discussion on X-ray tubes and also the production of X-rays. Specifically, we will look at this part of an X-ray generator, the circuit side, so the electrical circuit, and we will consider the components that are responsible for the generation of X-rays or providing the necessary environment for X-ray generation. And we will consider how they function in that whole process. So let's begin. The first component that's quite important and will always be present in the context of X-ray generators is the power source. This is related to what the power supplying company gives to either our hospital or where our practice is. So typically you would have a power source which should usually meet the requirements of the operation of our X-ray generator according to spec. What's pictured over here is a 220 volt single phase power supply. We will talk a little about what single phase means, but for now we just know that what's pictured in this particular example of an X-ray generator is a 220 volt single phase. It is useful to know that power supplying companies, for the sake of transmission of electricity, they supply what is known as alternating current. And this alternating current is used in X-ray production. So the point is our power source would typically be providing us with alternating current. So the power source supplies the power, but in what form? It will be in alternating current. In the pictured example, the type of source is a single phase. Single phase means we only have one signal of alternating current. And note, this current is first moving in one direction. Notice it's got a positive voltage. But then on this part, it's moving in the opposite direction. So if this was moving forwards, this would be moving backwards. Hence the name alternating, because for a given frequency, the power, the direction of the flow of electricity would be changing. How fast it changes depends on the frequency of that signal. If you look at your wall plug, it might say 60 hertz. That means the power, the signal, the AC signal is changing direction 60 times a second. That's beyond the scope of our discussion. This is just to give you an example of what type of alternating currents we may find. We just had a discussion on the single phase. Single because one signal is supplied. Now, the other option, which is typically what we find in our everyday life, is the three-phase AC. Three-phase because there are three signals. And these signals are out of phase by 120 degrees. Let's go back to the single phase. Notice the single phase, we begin with zero electricity, zero current. In this case, we're plotting voltage, so we begin with zero voltage. Notice our voltage increases until it reaches a peak. This is where we would like to keep the power. We want to be operating where the voltage is at its peak. But then the kind of electricity supplied to us doesn't always remain at the peak. It drops eventually back down to zero and then begins to move the other way. Now, how can we try to stay as much on the peak as possible? This is the role, or this is the reason why we have three-phase electricity or three-phase alternating current. So you might notice as the blue signal is descending, the red signal is rising. And when the red signal begins to decrease, the yellow signal rises. So effectively what this means is our machine will be operating very close to the max. This kind of a decrease and increase, this kind of a wave, this is known as a ripple, the ripple. It's not ideal, but it's better than going from the peak and all the way back to the minimum or the zero. So although we're not operating at a maximum point here, we are at least keeping our power quite high. So these are the different kinds of supplies that we can expect from our power source. Okay, then the next component is what is known as an autotransformer. An autotransformer first is a transformer, and a transformer is an electrical device which is passive. That is, it doesn't have any active electronics, but it's passive. But what it does is it serves to change the voltage amplitude and also the current amplitude. So although our power company might promise to supply us 220 volts, sometimes it might be supplying us slightly more than 220 volts and sometimes slightly less than 220 volts, but on average it will be 220 volts. But our machine was designed to operate at exactly 220 volts. So then how do we compensate for that excess voltage or that shortage in voltage? This is the role of an autotransformer. A transformer will increase the voltage as necessary if it's too low, or decrease it as necessary if it's too large. An autotransformer is also known, it's called an autotransformer because it uses the principles of self-induction. This is an electromagnetic principle. It's known as self-induction. And the properties of an autotransformer, although we'll talk about them later, I'll just highlight them now, is that it has a single set of windings, which means it also has a single core. I will contrast this later with the other transformers. As you can see, there's one set of windings here and another set of windings here. This is a typical transformer, but over here with the autotransformer, there's only a single set of windings. And how it works is that it uses tabs. The tabs could be, or rather the circuit could be completed at any one of these tabs. The tabs we select, we could either include more windings in the total, in this autotransformer, or we could exclude some windings. By including more windings or excluding some windings, we therefore affect the voltage. So that's what the autotransformer is useful for. It's useful for compensating for any voltage fluctuations we may have. And furthermore, the autotransformer allows us to select our kilovolt peak. You might notice that over here we have something called a kilovolt peak. Actually, this kilovolt selector is operated by means of the tabs of the autotransformer. We will talk a little more about the kilovolt selector, but right now it's just that what's important is that the autotransformer enables the kilovolt selector to operate. And finally, the autotransformer, once the autotransformer has adjusted all the shortages and compensated everything so that we get exactly 220 volts, it therefore provides the signal to the rest of the X-ray generator, to the rest of the machine. All the other components will receive the power from the autotransformer. So that's what the autotransformer is useful for. It compensates for any voltage fluctuations from our input source, since we have no way of making sure that we're always getting 220 volts. And it also enables us, it enables the function of a kilovolt selector, and then it will transmit the power to the rest of the X-ray generator, to the rest of the X-ray machine. So that's the autotransformer and its functions. Next, we talk about the controls which the radiographer or the technician has at their disposal. The first one, which is fitting, is the KV selector. This is where the technician may select how much, what the kilovolt peak should be for a particular exposure. That obviously will be dictated by the anatomy that they are scanning, how penetrable it is. So if we need high energy X-rays, then the technician would employ this device, the KV selector, to make their selection for the given exposure. And moreover, the technician has at their disposal what is known as an MA selector. Of course, MA is the milliamps. This is where we select our tube current. Once this is selected, this will dictate how many electrons are emitted toward our target. That is all selected on this device. It's part of the console. And then finally, the other important control is the exposure timer. So not only are we interested in how much energy should these X-rays have and how many we would like to produce, so this is how much energy should they have and how many do we want to produce, but also for how long do we want to produce them for. So these three parameters are to be selected by the technician, and they do so by using these controls. Okay. It is actually quite important for us to realize that the KV selector is the one that dictates what the maximum energy of the electrons is going to be. The electrons that are emitted from the filament and that are headed toward our target, they're going to have a certain amount of energy, and that energy is dictated by what we choose on our KV selector. But remember, the more energetic the electrons are, the more energetic X-rays we're going to produce. So effectively, our KV selector is effectively is where we decide the kind of electrons we want, the kind of X-rays we would like to produce. The higher the selection on the KV selector, the higher the energy selected on the KV selector, the more energetic, or the higher the energy of the X-rays that will be produced. And obviously, the higher the energy of the X-rays, the more penetration the more the depth of penetration of these X-rays. Okay. And of course, we've also mentioned the matter of time. How long would we like to carry out this exposure for? This is dictated by our exposure timer. So if we select to expose, to perform a scan for a certain amount of time, this would be selected over here. If you choose 2 seconds, 5 seconds, or however the right order of magnitude, that will be decided by the selection in the exposure timer. And then finally, the MA selector, this dictates the tube current. Remember, the tube current refers to the amount of electrons that are being boiled off or rather the electrons that are traveling from the filament to the target. That is our tube current. And that tube current is selected effectively over here with the MA selector. The more electrons, or rather the higher the current, the tube current, the more electrons would be traveling from the filament to our target, which means if there are a lot of electrons bombarding our target, that means the more X-rays, that is the quantity of X-rays of being produced, it also increases. It should be emphasized that this refers to quantity of X-rays produced because there's more electrons being produced. But over here, we're referring to the quality of our X-rays. How much energy do they have? How much can these X-rays, how deep can they penetrate into the tissue or the bone or the anatomy? But here, how many are they being produced? So you might think of this as the intensity, while this as the energy. How much energy, how energetic are these X-rays? And coincidentally, we'll be able to figure out how much energy is being spent during an exposure by these three properties. These three properties tell us how much energy is being deposited during the whole exposure. This is the kV selector, or the selected kV, that's the kilovolt peak, times the MA, that's the amount of electrons, times how long we've been carrying out the exposure for. This product of these three properties tells us the energy that's being used in the whole process. Effectively, we should be able to therefore predict what thermodynamical changes we expect on either the target or the X-ray machine. This will enable us, again, this is where thermodynamics comes in to help us understand how our machine will behave under a certain exposure. This is where we can figure out whether our machine can be used for certain exposures, even before operating the machine. We don't want to overexpose our machine, effectively damaging it. So it's quite an interesting fact that, again, as I've mentioned earlier, that thermodynamics plays a very important role. It comes up also in X-ray tubes. Okay, so those are the controls. These are found on a console where the operator can set the parameters necessary for the exposure before beginning the exposure. And also, it should be noted, maybe let's go on to the next component, and then I'll highlight the note. So the next component is a high voltage transformer. What's important again here is that we have a transformer. It's called high voltage because this transformer takes the signal, the AC signal on this part of the circuit, and it amplifies it to high voltages. So whatever signal we had here, which came in from the power supply, made it through our auto transformer, and then eventually made it to these windings of our high voltage transformer, will be amplified. It will be increased so that what comes out of this side on these wires will be high voltage AC. It would be amplified by some factor. We will get into the details of what that factor is later on when we talk about transformers. But the point is, what the output of this transformer is going to be high voltage electricity or current. And this is the current we need to accelerate electrons from our filament all the way to our target. This is where we apply that high voltage that accelerates the emitted electrons all the way to the so that they bombard the target, and that's where we get the Bremsstrahlung radiation and also characteristic radiation. The guy responsible for providing that high voltage is this high voltage transformer. This high voltage transformer is sometimes referred to as a step-up transformer. This is a generic name for it. Step up because its output voltage is larger than its input. So in this example, it may have, on this side of the circuit, we might have 220 volts, but on the output here, we might have maybe 1,000 times the output. It might be, 220 kilovolts. So we started off with 220 volts, maybe the output might be 220 volts, 220 kilovolts as an example. The point is, it increases the voltage, hence it's called a step-up transformer. In increasing the voltage, this transformer does the opposite with the current. While the voltage is going up, is increasing, the current decreases. The current through it is decreasing. This is a property of transformers. When it amplifies, when it increases the voltage, it decreases the current, and when it decreases the voltage, it increases the current. We will see this example where these changes are reversed when we talk about the filament transformer. Again, this transformer is responsible for providing the high voltage, which high voltage accelerates the electrons from our filament to our target. This is very, very important. Without this transformer, we will not be able to produce high energy electrons through which we can have Bremsstrahlung radiation when these electrons slow down, or when these electrons knock out an inner shell electron so that there's characteristic X-ray radiation. So this guy is very important to our ability to produce X-rays. Okay, I have already alluded to this, that we will talk about the filament transformer, and this is the prime opportunity to talk about it. And here it is over here. Box in this red box, or rather box in red, is what is known as a filament transformer. This transformer here is the one that's connected to the filament from which we thermionically emit electrons, which electrons therefore are accelerated toward the target by means of the high voltage transformer. This transformer does the opposite of what the high voltage transformer does. Specifically, it decreases the voltage. But as I've mentioned, when a transformer decreases the voltage, what it does for current is that it increases it. So decreasing the voltage, increase the current. Because it decreases the voltage, this filament transformer is also known as a step-down transformer. Step-down because the output voltage is smaller than the input voltage. That is, the voltage that came in through here, through this part of the circuit, is going to be larger than the voltage that comes out through this circuit. And obviously, this means because the voltage is decreasing, the current is going to increase. And in the filament side, that is these wires, we want the current to be large. Because when the current is large, this means we'll be able to boil off more electrons. The higher the current, through a wire that has a resistor, which our filament has resistance, this resistance will cause friction, which means electrons are going to, which means the filament would heat up, and when This means the filament will heat up, and when the filament heats up, this provides, the temperature rises. When the temperature rises, the electrons on the surface of our filament, they begin to be emitted. This is how the process of thermionic emission is accomplished. It is accomplished by providing high current on the filament circuit. I will explain what the filament circuit is later on. Right now, it's not important, but that's how thermionic emission is accomplished. It's accomplished by this step-down transformer, which reduces the voltage and increases the current. And that current is therefore responsible for causing thermionic emission. Okay. So all of that is summarized in this slide. So we have thermionic emission by virtue of the increased current through the filament. Okay. And then the next important component is what is known as a rectifier. Before we talk about a rectifier, I would like to bring something to your attention, or maybe let me pose it in a way of a question. Did you realize that inside of an X-ray tube insert, electrons always flow from the filament to the target? Electrons don't flow backward. They always flow this way. They never flow backward. But the current supplied to us by our power supplying company is alternating, which means it goes back and forth. So how then can we use current that goes back and forth to produce electrons that go in one direction? This is accomplished by a device known as a rectifier. A rectifier is an electrical device that's used to convert alternating current, that is current that goes back and forth, that oscillates back and forth, to DC. DC is direct current, that is current that flows in one direction. This is why a rectifier is necessary, because inside of an X-ray tube, electrons only flow one way, which means electricity only flows one way. Therefore, we need to be able to convert our AC signal supplied by a power company to a DC signal. And the pictured rectifier here is known as a bridge rectifier. We'll talk about it in a little more detail later. But it's made up of diodes. Diodes here, these symbols are electrical symbols for a diode, as you might recall. Diodes are devices that allow the flow of current only in one direction. An ideal diode only allows current to flow in one direction and never backwards. So you can think of it as an electrical valve. It's something that, one-way valve. So it allows current to flow in one direction, but never in the opposite. Of course, that's an ideal diode. You might notice here that we have diodes, actually 4 of them. They are arranged in a particular way. This collective system, or this collective arrangement configuration of the diodes, is known as a full bridge rectifier. Sometimes it's called a full wave rectifier. So that's one kind of rectifier that can be employed. Another kind that can be found is a half wave rectifier. Actually, strictly speaking, a diode is a simplest kind of a rectifier because it allows current to flow only in one direction, effectively converting an alternating signal to a DC signal. So when electricity flows one way, it will allow it, but when electricity tries to flow backwards, the diode will prevent it from doing so. So a diode is it's the simplest rectifier we have. And of course, as I've mentioned, that our rectifier provides DC signal. allowing the electrons to always flow from our filament all the way to our target, which target will therefore produce X-rays. So those are the important components that make up almost every X-ray generator, the most basic. It should be noted that with different models and different makers of X-ray generators, we might find more devices, some of which are supporting, some of which are, because of modern technology, they simplify the process. But the ones we have spoken about right here are the most basic. So let me highlight some basic, I shouldn't say no basic, but additional components which help make the exposure, the X-ray imaging easier. For instance, over here we have an MA stabilizer. That may not be found in all the devices we have, in all X-ray devices, generators, but in this particular example, we have an MA stabilizer. And notice here, we also have a focal spot selector. Not all devices have a focal spot selector, because some of them only have one filament. So there's no option to choosing between the short filament, that is the small filament, or the larger filament. So my point is these parts may not be present in all the X-ray generators we come across. And moreover, some other useful, helpful additions are these measuring devices. This is a voltmeter. What it does is it's a way for us to check whether what we have selected here is truly what's going on in the actual circuit. For instance, suppose in our KV selector we choose 110 kilovolts. We want to produce, we make a selection of a KVP of 110 kilovolts, but then it's always good practice to make sure we truly have 110 kilovolts through our circuit. So we have a voltmeter to measure that. The same goes here. This is an ammeter. This is a device that measures how much current is going through. Well, this MA, we may have set a particular MA here, but it's good practice to check whether we really are getting that selected MA. It might be that our signal from the power plant has fluctuated way beyond what the auto transformer is able to compensate for. So we might be running at a slightly lower kV or sometimes slightly higher. We don't want to unnecessarily overexpose a patient, and also we don't want to operate our X-ray machine when we're not getting optimal X-ray photons. Okay. It is also helpful to realize, this is just terminology, that this area that's boxed by the red box is also sometimes referred to as a filament circuit. A filament circuit. It is its own sub-circuit, which includes the filament from which we emit or thermionically emit electrons. So you might find some texts that refer to the filament circuit. What they're referring to is this bottom half. Of course, not including this high voltage. So our box should be slightly low. It shouldn't include that part. As you might notice that in the middle here, especially as dictated by this high voltage transformer, we have what is known as a primary side and also the secondary side. Sometimes these are referred to as the low voltage side. That's what the primary refers to. And the secondary is also sometimes referred to as the high voltage side. The reason is The low voltage side is the side where it is safe for us to make the necessary exposure settings. Once those settings have been set in place, then we can use the high voltage transformer to produce the high voltages necessary for X-ray production. The reason why we make this kind of a distinction is for safety reasons. This is where the technician may safely operate, but over here we prefer that the technician would not be present. We don't want to make changes on this side of the circuit because it's high voltage, and should anything go wrong, both the machine and the technician would be at a risk. So we usually make adjustments on this side of the circuit, that is the primary, and then all those settings can therefore be amplified on the high voltage side. Okay. And all of this, should you seek more details on how the X-ray circuit operates, over here I have attached an article which summarizes everything I just spoke about. So I commend, should you have further questions, you consult this article. It's accessible, and this would mark our conclusion of our discussion on X-ray circuits.